It's really been, excellent day, and we've had some excellent presentations. So today we're joined by David Pizzi and Kyle Schauer. They're both with Tetra Tech. After the presentation, if you guys have questions, please just put them in the chat, and Brad, my co-host, will read them off. But today they're going to be doing a presentation on the analysis of sedimentation and fish passage on the Rio Grande. So with that being said, I'll let you guys, I'll hit record here, and I'll let you take it over. Thank you.
Thanks, Thad. So good afternoon. I want to thank all of you for your interest in this technical seminar about the ongoing analyses of sedimentation and fish passage that we are conducting on the Rio Grande at the Isleta Diversion Dam. I also want to thank the SAME Rock Island Post and ASCE for providing the opportunity to share this information with you during this training conference. We are targeting 40 minutes for our presentation, followed by 10 to 15 minutes of questions and answers. And if you've got a question as we're going, please note the red slide number in the upper right corner so we can easily return to the slide. So my name is David Pizzi. I'm in my 19th year with Tetra Tech, working as a hydraulic engineer. I've been working for the Pueblo of Isleta on the Isleta Diversion Dam, or IDD, settlement for the past 4.5 years, primarily working on solutions to the sedimentation issues and supporting the fish passage solution. Because of a last-minute meeting with tribal leadership, Derek is going to be unable to join us this afternoon. He was excited to share with you all the project background. In his role as the Water Resources Department Manager for the Pueblo, he is the Pueblo's liaison with the settlement parties, and he is the Pueblo's project manager. To save you all from having to listen only to me for this whole presentation, my coworker Kyle will be divvying up the topics to share with you. Kyle has been working on sediment transport issues with the Pueblo of Isleta since 2012, most recently with Derek on the sedimentation and fish passage issues at the IDD. So this outline shows the topics we'll cover today in the seminar, and it provides you with a breakdown of the time targeted to each topic. I'm going to start off covering the project background for Derek. The Pueblo of Isleta is our client, and it's one of 6 pueblos, each a distinct tribe along the southerly flowing Middle Rio Grande in central New Mexico. The red star identifies the project site, which is about 10 miles south of Albuquerque. In 1923, the New Mexico legislature provided the legal framework for the organization of the Middle Rio Grande Conservancy District. And a component of the district's mission is to operate, maintain, and manage irrigation in the Middle Rio Grande Valley in cooperation with other local, state, and federal agencies. So in support of this mission, by 1935, the district had constructed the Isleta Diversion Dam to supply irrigation water to farmlands on both sides of the valley. At the time the dam was constructed, which corresponds to the green lines shown here, the river was notably wider than its current condition. The Isleta Diversion Dam was constructed at a natural geologic constriction shown here on the topo map, with the Pueblo on the west bank, the historical village on the west bank there, and it's reflected by the Pueblo of Isleta's name, meaning little island, because the village sits above the elevation of the adjacent floodplain. Whereas the dam site was originally a constriction that naturally limited potential for sedimentation because flood flows accelerated through the constriction, river narrowing has turned the site into a relative expansion that exacerbates sedimentation. So the yellow polygon here is the 1962 channel, and it's representing the geomorphic change that occurred for about the first 30 years, the river narrowing after the diversion dam was constructed. It's also notable that the Isleta Diversion Dam diverts flow through sluiceways into irrigation infrastructure on both sides of the Rio Grande. And we preliminarily estimated that the cost of a project to narrow the river through the dam site to better maintain sediment transport continuity was going to be well in excess of the available funding, largely because of the effort that would be required to relocate a sluiceway and a canal heading. So for some historical perspective, there were disastrous back-to-back floods in 1941 and 1942 that nearly bankrupted the district because of the extensive maintenance backlog from the flooding. So in the Flood Control Act of 1948, Congress authorized the Middle Rio Grande Comprehensive Plan, which transferred ownership of the dam to Reclamation, with the district maintaining responsibilities for operation and maintenance. And the act assigned Reclamation responsibility for rehabilitating the damaged dam. So in the mid-1950s, 50s, Reclamation rehabilitated the diversion dam, as shown in this photograph, to address in part settlement of the dam that was driven by seepage under the foundation. In this image here, the one at right, it is 1962 USGS imagery. And at the top of the photo, we can see the eastern side of the Isleta Diversion Dam, the upper end of the Peralta Main Canal, and then where it turns south past the dredge spoil piles, the canal notably widens, and at the downstream end in the red box, we can see a mudcat dredge. And that is zoomed in here, the picture to the near left. The dredge had a floatable pipe that then connected into fixed pipes. The fixed pipe, as of today, is shown here on the far left picture, and it pumped the silt and sand to the spoil areas for dewatering. And so even 60 years ago, when this image was taken, sedimentation in the canals, particularly these east side canals, was an operational issue that really complicated reliable deliveries to irrigators. So if we come forward to today, or near today, this picture from the summer of 2019 shows extensive dredge spoils along the head of the Peralta Main Canal. And they're put there to dewater, and these dredge spoils just confirm that, you know, even today, sedimentation remains a huge operational challenge for the Conservancy District. At the start of our project, there were legacy dredge spoil piles along canals on both sides of the valley, shown here by the yellow and the pink lines. And these spoil piles had accumulated over decades of canal dredging. So the figure shows that the sedimentation in the canals, it's not limited just to the canal headings at the Isleta Diversion Dam. The sedimentation issues persisted for miles down canal from the headings. In addition to the sedimentation impacts, the operation of the diversion dam has impacted endangered species. In 1994, the Rio Grande silvery minnow was federally listed as endangered under the ESA, in part because diversion dams, such as the Isleta Diversion Dam, fragment their habitat and prevent migration during the summer low flows and river drying. So in 2003, the U.S. Fish and Wildlife Service issued a jeopardy biop on the effects of the actions associated with reclamations in the district's water operations and river maintenance and the Corps' flood control operations. And it was the 2016 biological opinion where the Fish and Wildlife Service required fish passage be implemented at the diversion dam. So with this kind of background understanding now of the history of the sedimentation and fish passage issues at the Isleta Diversion Dam, how was a settlement agreement reached? Well, the Pueblo contended that it had valid claims against the U.S. and the district in connection with the construction and operation of the Isleta Diversion Dam and the associated irrigation and drainage facilities. Reclamation and the district disputed the validity and the amounts of these claims. Fortunately, all the parties wished to avoid litigation, so they entered into an agreement of compromise and settlement. And the parties, the Pueblo of Isleta, Reclamation, the Middle Rio Grande Conservancy District, and the Bureau of Indian Affairs, executed the agreement in October of 2016. Components of the agreement that bear on this presentation include infrastructure improvements, such as projects and activities to minimize the operational problems at the diversion dam associated with sedimentation, improving fish passage at the diversion dam, and restoring bosque, which is just the Spanish word for forested riparian floodplain, the bosque and riverine habitats along the Pueblo of Isleta reach of the Middle Rio Grande. The agreement also empowered a technical team to evaluate current operations at the diversion dam and the related irrigation facilities, and to recommend technical approaches for addressing operational and maintenance issues. So Kyle and I are members of the technical team on behalf of the Pueblo, and I'm going to turn the presentation over to Kyle so he can share with you the preliminary engineering and analysis, which is sometimes referred to as the PAIR, completed to identify and screen options for addressing the sedimentation and fish passage issues.
Thanks, Dave. We performed preliminary engineering analyses at the beginning of the project to understand existing conditions, develop and assess options for fish passage and sedimentation management, and inform the need for additional analyses. The existing conditions analyses included an evaluation of fluvial geomorphology, an inspection of the electrical, mechanical, and structural components of the dam, sedimentation at the project site, sediment delivered to the project from further upriver, and an examination of nearby fish passageways. Once we had a decent grip on existing conditions to understand the nature of the problems and the capacity of the dam's structural integrity to accommodate different infrastructure improvements, our focus shifted from developing and screening conceptual level options for improving sedimentation management. Working with the technical team, we brainstormed 35 sediment management options, and this is a pretty thorough process. Then we screened the options to remove ones that didn't satisfy all of the goals of the settlement. Remaining options were then ranked based on evaluation criteria that considered factors like environmental impact complexity, costs, adaptability, and relative magnitude of sedimentation reduction. We identified knowledge gaps during this process, which were used to make recommendations to the technical team about additional data collection and modeling so that the technical team could select a preferred option from the top ranked options that came out of this process. We focused on evaluating options that targeted reducing the sedimentation problem on the east side, because that's where the sedimentation was more problematic and impacted reliable delivery of irrigation water. The process included development of conceptual design plans and accompanying cost estimates to help rank the options. And not to give any spoilers here, this ultimately came to the top as the preferred alternative. So it involves excavating this bank line and making a sloped bed in this sluiceway. And we were really excited that the process ultimately proved, was justified by the fact that this option was relatively simple and ultimately will show you very effective. So because the 2016 biological opinion required fish passage for the silvery minnow, we also looked into options for providing fish passage. The interesting thing is it's a bit of a unique situation in that there's not a lot of studies that discuss how to pass small-bodied fish. I mean, the minnow is 2-3 inches long on average. So like we did with the sedimentation management, we worked with the technical team to brainstorm 13 different fish passage options that were then screened based on the goal, settlement goals, and then ranked based on evaluation criteria. There's fewer options here because of all the infrastructure constraints. If you remember back a few slides, they're taking water off at both sides, so it's difficult to go around the dam. Some options were recommended prior to the existing conditions analyses, the 2016 biological opinion, or clarifications that we subsequently got from the Fish and Wildlife Service. For example, the option above allowed me to sneak a comment into the preliminary engineering report about our lack of understanding and need for additional research into the type of elevator music that silvery minnow preferred. In March of 2020, Reclamation led a value planning study of some of the top options, and we found that those top options, many of them remained tightly clustered in scoring, indicating that other factors, such as Pueblo's preference to minimize cultural and traditional impacts near the dam, would drive the selection. So we recommended further consultation with the Pueblo. Ultimately, 2 fish passage options rose to the top. Both fishways go through an existing gate bay in the middle of the dam. The downstream, one is placed largely upstream and one is placed largely downstream. The downstream fish passage option was quite a bit less expensive to construct because you're not trying to protect a concrete apron that went in as part of the 1950s rehabilitation to prevent piping underneath the dam. However, there is an important cultural site that is regularly used by the Pueblo downstream of the dam. And so there was a lot of concerns about whether that would impact their use of the site. The Pueblo recently provided unofficial approval of the downstream option, which is pictured in this plan view here. We anticipate that this will become the preferred option. It's a technical fishway, like I said, located primarily downstream of the dam. The fishway will control hydraulics through a series of cylindrical baffle chevrons, which are these circles that you see in the channel. And that will provide sufficient low enough velocities and sufficient rest areas to allow passage of the Rio Grande silvery minnow. However, because we are wading into some new waters with these little minnows, we want a way to evaluate how successful it is and then adaptively management. Pit tag antennas will be constructed into this passageway to allow for monitoring of the movements of tagged fish. We evaluated existing environmental permitting authorities that might apply for the implementation of sedimentation and fish passage improvements, particularly considering anticipated environmental compliance needs such as NEPA, ESA, Clean Water Act, and cultural compliance. We also compiled compliance documents from the Pueblo that they've completed in the last 15 years to provide background information that may be used as reference for environmental compliance required for construction of the preferred options. We completed these tasks also in close coordination with the technical team. One of the important findings of the preliminary engineering and analyses was that sediment management options could not be effectively ranked because of a lack of understanding of sediment transport processes near the Isleta Diversion Dam. We recommended additional research by asking the following 4 questions. First, why is sedimentation on the east side canals more problematic than the west side canals, despite the fact that they divert, I should say, comparable flows? Second, whether sediment diverted into the irrigation canals enters the sluiceway from near the bottom of the sluiceway or higher in the sluiceway water column. Some options are better suited to remove bed load, which stays near the bottom of the water column, while others are better suited to remove the suspended load that obviously can move much higher in the water column. The answer to this question was instrumental in selecting a preferred option. The third question, how will sediment excluded from the canals impact the morphology of the Rio Grande downstream of the Isleta Diversion Dam? That's an important question because adjacent to the cultural site, that's only a few hundred feet downstream, the Pueblo has invested quite a bit of money into constructing and managing a fairly large restoration site that they don't want to become impaired in the future. Fourth question, how will gate operations affect diversion of sediment into the canals? We recommended data collection, scaled physical modeling, and numerical modeling to answer the questions. And Dave is going to start off by talking about how these recommendations were implemented.
So the pair, or the preliminary engineering report, recommended the data collection to support model development, testing, and calibration, and to increase our knowledge of existing sedimentation around the IDD, and also to inform designs of the infrastructure improvements. So since 2015, just like Kyle was saying, we have been monitoring a channel restoration project immediately downstream of the dam. And the monitoring includes cross-section surveys, vegetation inventory, and listed species surveys. So in 2017, for the Bureau's Albuquerque area office, we surveyed the bathymetry using RTK GPS and the floodplain topography using LiDAR for a mile upstream and downstream of the dam. The resulting surface is shown here at right. And the preliminary engineering recognized the value in building on these previous monitoring efforts to focus on future measurements of hydraulics and sediment transport into the sluiceways. So the district started recording gate operations and gate settings for the main stem dam radial gates, the sluiceway gates, and the canal headworks during the 2019 irrigation season. And the spring runoff for 2019 was projected to have a high peak flow and a sustained duration. So two conditions that are ideal for mobilizing and transporting sediment. So the technical team agreed to prioritize that opportunity to measure hydraulics and sediment transport. The technical team agreed with the proposed plan for these measurements, and we targeted May and June in hopes of capturing the peak of the runoff, which, with the benefit of hindsight, now we're looking at the hydrographs here. And the technical team funded 3 one-week-long rounds of measurements. Those are shown by the pink rectangles, when flows in the river were between about 4,500 and 5,500 CFS. And we were able to leverage a relationship with the USGS's New Mexico Water Science Center to accurately and economically complete all of the laboratory analyses of sediment masses, concentrations, and gradations. So this figure shows the 14 agreed upon locations where we collected hydrographic measurements during the 2019 spring runoff. And you can see that there's a location upstream, a couple locations upstream of the dam on the river, one downstream. There's the inlet and outlet of each of the 2 sluiceways, and then measurement locations in the canals heading at the dam. So we used our acoustic Doppler current profiler, ADCP, mounted in a kayak to measure flow in the Peralta main canal. And we also mounted it in a trimaran so that we could measure flow in the sluiceways. These were places where we didn't have good information on flow rates. We also collected bed material samples from the canals and from the river. And here you can see that there was active dredging that we were working around. So we had to coordinate closely with the irrigation district to ensure the safety of our personnel and theirs. We measured bed load transport using handheld and cable deployed samplers. So where flows were too deep or swift to safely use handheld instruments, we use cable deployed samplers. In this case, either from the Highway 147 bridge, shown here at left, which is just upstream of the diversion dam, or from one of our smaller boats, shown here at right. We used handheld depth integrating samplers to measure suspended sediment concentrations here in the west side Belen Highline Canal. And we used cable deployed samplers to measure depth integrated suspended sediment concentrations. That's the picture on the left here with the brass sampler, or point suspended sediment concentrations. That's the equipment shown here on the right. And we wound up collecting quite an extensive set, or 3 sets of measurements. And it was the interpretation of these measurements that really crystallized for us kind of a eureka moment in understanding why the east side sedimentation issues have been historically so much more problematic than on the west side. And it's largely the turbulence in the east sluiceway. So it's that understanding we gained from this effort that really guided the development of the structural modifications that we were considering for the East Sluiceway. And these modifications were evaluated using a physical model. I will share with you our involvement in the testing and analyses with that model, but I'm going to turn it over to Kyle next to talk to you a little bit about some of the numerical modeling we completed.
So we completed 2 types of numerical modeling for this study. One, they were both sediment transport analyses. One was a 1D model, and the other was a 2D model. So 1D modeling was used to estimate the supply of sediment to the Isleta Diversion Dam from further upriver. And the 2D modeling was used to assess the impacts of a range of different gate operational scenarios on sediment diverted into the sluiceways. The 1D mobile bed model was previously developed using Hydrographs for the Albuquerque district. We completed this model in 2008 after a period of collaboration and beta testing with Stanford Gibson at HEC. The 2D model was developed for this project specifically using SRH2D. This afforded us a good opportunity to work with SRH2D developer Young Lai, who sits at the Denver Technical Service Center, which is represented on the technical team. Young Lai is now beta testing functionality to route sediment through radial gates like we have at the Isleta Diversion Dam. The USGS Gauge at Central Avenue in Albuquerque on the Rio Grande has a robust long-term record of suspended sediment transport measurements. We use this record to develop a record of total bed material load, which is the bed load plus the sand size fraction that's suspended, using the Bureau of Reclamation's modified Einstein procedure. So the software package is called BORA-MEP. The only problem is that this gauge is located 14 river miles upstream of the Isleta Diversion Dam, and the river tends to be depositional between the gauge and the diversion dam. Thus, we used the 1D mobile bed HEC-RAS model to route that total bed material load series from the USGS gauge to the Isleta Diversion Dam by size class. It was important to have this information by size class because it informed operation and maintenance cost estimates, because we knew what was getting diverted into the canals by size class. And it was used for developing boundary conditions to the 2D model. Because it was more economical to develop a physical model of the full river and all 29 main stem gates, the SRH2D model was developed to evaluate the different gate operations. The model was set up to include all of the main stem gates, the proposed fishway, the 7 diversion gates, and the 2 sluice gates at the end of the sluiceways. While improved gate functionality is being developed and tested by SRH2D, the model was set up to have an exit queue, if you're familiar with SRH2D. Basically, it's a specified flow boundary condition at each gate. Then the number and location of open gates were varied to evaluate how those changes impact changes in bed material flux into the sluiceway. So this process is ongoing and will eventually be completed for a range of flows and operational scenarios. But this is an example of the results that we're getting out of the SRH2D model. The blue line in this graph shows sort of baseline sediment flux based on the information we got, operational logs from the MRGCD, while the gray line shows the sediment flux for an alternative gate operation scenario. So then the green line represents the cumulative difference between these scenarios. We can use these plots to help the Pueblo develop operational strategies to incrementally reduce sedimentation above and beyond the preferred sediment management option. Dave will now discuss how we use the physical model to better understand sediment dynamics in the sluiceways.
Excuse me. So what we realized was that with the turbulence, the numerical modeling software for the sluiceways, even CFD software, was not yet reliable enough for accurately representing the sediment dynamics that we needed to quantify. And so what we're seeing here in these pictures at left is the east sluiceway facing downstream. And you can see the boils in the water surface that are indicative of the turbulence of the flow moving through the sluiceway. A comparable flow condition and diversion volume is shown here on the right for the west sluiceway. And you can see that there's none of those boils. So the flow is much more quiescent and doesn't exhibit any of the turbulence that we're seeing on the east side. So the turbulence was clearly the primary driver behind the technical team's choice to proceed with a scaled mobile bed physical model that was ultimately, it was designed, constructed, and operated at Reclamation's hydraulics laboratory at the Technical Service Center here in Denver, Colorado. And this location was relatively close to the project site. So pre-COVID, we thought this was going to be the ideal way to allow stakeholders to frequently visit the model. Our design started in early of 2020 when construction of the model began in July 2020. So most of the simulations were carried out in COVID, which really impaired the ability to have stakeholders come up and visit the model. The model design relied on Froude number scaling, which is the ratio of inertial to gravitational forces. It's kind of the standard for scaled physical models for the hydraulics of them. And the sediment gradation was scaled to preserve Rouse numbers, which are the ratio between fall velocity and shear velocity. So the red outline here shows the footprint of the 1 to 8 scale physical model. And because flow depths are relatively shallow, given how wide the river is, it was important to have a large scale model to keep Reynolds numbers up. And so the 1 to 8 is relatively large, but it meant we could only get 10 of the 30 main stem dam gates within the model. So just note the angled orientation of the dam here. And now we're looking facing upstream in the what we call the bathtub in Reclamation's lab. So the green foam here is the base of the diversion dam, and the bathtub is roughly 30 feet by 100 feet long. The Reclamation used 3D printers to fabricate some of the geometrically complex parts of the model, such as the main stem dam radial gates shown here. 2 large pumps were used to recirculate water and sediment. So the gray roll-off dumpster at right was set into the sump to keep the recirculated sediment from mixing with the rest of the laboratory's water supply. Hopefully we got a video or two here that these work well enough for you. We used dye for the hydraulic testing before sediment was added to the model. And this was a really important step to make sure that we were able to observe in the model some of the vortices and turbulence that we observed at field scale. Fracking sand was used for the scaled sediment gradation, and the storage of sand in the bed of the model was the supply, the source of the sediment supply for each test. We compared depositional patterns in the model to observations. So here we are facing downstream into the East Side Canal headworks across the East Sluiceway. And the depositional patterns in the sluiceway closely aligned with our observations, which really increased our confidence in the ability of the model to reliably reproduce the field scale conditions, including the turbulence at the entrance and throughout this sluiceway. So Reclamation created these mixing boxes that allowed all of the sediment that was in transport to be measured continuously using acoustic backscatter sensors that were wired into a laptop, along with sensors of water levels and flow rates. And the laptop converted all of the scaled measurements to field scale values, which was great for stakeholders so that they could relate the numbers they were seeing in the model to their real world experiences. The modular nature of the model facilitated testing many of the potential modifications. So here we tested a lengthened sluiceway inlet to see if we could move turbulence away from the canal headworks. In this picture, you see a widened sluiceway inlet, and this configuration actually required removal of one of the main stem radial gates and a pier. In this figure, the brown dashed line indicates the alignment of the existing bank of the river. And you can see here that the realigned bank better aligns flow that will be approaching the sluiceway with the orientation of the sluiceway. And eliminating some of those bends in the flow substantially reduced turbulence and canal sedimentation. So this figure shows the performance of just a few of the tested sluiceway modifications, shown here by the colored lines. And we evaluated the ratio of suspended sediment concentration, that's shown here on the y-axis, in the canal headworks. So that's the CH, H for headworks, to the river, CR, as a function of the sluiceway exit gate opening, which is shown here along the x-axis. So a ratio above 1 means that there are higher concentrations of suspended sediment entering the canal headworks than were transported in the river. And that is a serious issue we learned with the baseline scenario of the existing conditions, which is shown here in green. So the orange line shows the substantial reduction in sediment concentrations into the canal headworks that were achieved by simply realigning that upstream bank to better guide flow into the sluiceway. So over the range of gate operations, the preferred option, which is shown here as the blue line, and like Kyle showed earlier, it couples the addition of a sloped floor to the sluiceway with the upstream bank realignment. It performed about 4 to 8 times better than the baseline. So the blue to green, the improvement there is an order of magnitude greater than the stakeholders expected was possible. So even though the preferred option, the blue line, didn't perform the best, which is shown here by the red line, representing the widened sluiceway, where we got rid of one of the gates and piers, the technical team selected the preferred option because it represented the best value in terms of performance and cost. So while the widened sluiceway shown by the red line performed slightly better, the cost was 2 to 3 times greater, and it carried a real concerning risk of scheduling uncertainties during construction. So despite the cost of the physical model being about $1 million, it was instrumental in identifying solutions to the canal sedimentation issue that ultimately saved the project millions of dollars. And so those savings are being allocated to additional canal modifications and operational improvements at the dam, such as gate automation. So where do we go from here? Well, we're currently supporting the technical team as the project progresses to a design build delivery method for the final design, the permitting, and construction of the preferred sedimentation and fish passage options. Reclamation is leading the completion of the NEPA process. The technical team is considering how best to operate the facility following construction, which is targeted for completion in the fall of 2026. And we are currently initiating development of an adaptive management program. So I'm going to now hand this back to Kyle so he can share with you the final component of the settlement agreement that we are currently pursuing, the bosque and riverine restoration.
So the purpose of the Bosque and Riverine Restoration and Implementation Plan is to support the settlement agreement by providing scientifically based recommendations. It's consistent with the Pueblo's cultural and natural resources goals for enhancing, rehabilitating, and if possible, restoring floodplain and riverine habitat along the Rio Grande through the Pueblo. We developed the plan's goals based on the Pueblo's goals conveyed during a series of meetings with traditional cultural leaders, tribal elders, the tribal council, the tribal's governor's office, various tribal departments, including natural resources, water resources, and public services, and open meetings with tribal community members. The key restoration goals resulting from these meetings included reducing wildfire risks in the bosque, protecting and enhancing wildlife habitat quality and diversity, and improving river floodplain connectivity. The Natural Resources Department staff reviewed these goals and identified a variety of different management actions that could be taken to achieve each one. The goals and the management actions were integrated. Actions integrate ecosystem function and processes to benefit both terrestrial and aquatic organisms. And I think that last part is important. The Pueblo members and even leadership were not too concerned with the silvery minnows and yellow-billed cuckoos. They're a bit more concerned about removing tangled, dense, invasive vegetation that is unsightly and is a wildfire risk, or they want to see more turkey and that kind of thing. So it's the challenge of this planning ahead will be to be working with the Pueblo's goals and to bring them what they want, but use the funding for the endangered species to also provide habitat improvements there. And so restoration then is a challenging endeavor for the Pueblo that will be most successful with monitoring and documentation. Thus, we recommended that the Pueblo develop a monitoring plan that defines success clearly. To advance this recommendation, the plan includes criteria and adaptive management triggers for all proposed management actions. We present the criteria as specific, measurable, attainable, relevant, and time-bound or SMART objectives. We compiled existing information and collected new data to create a GIS database to visualize assigned management actions for various restoration concepts to explicit locations throughout the about 2,200 acre river floodplain corridor within the Pueblo. The implementation strategy will be phased out over the next 10 years to achieve every one of these objectives. We prepared a planning level cost estimate of about $11.5 million to implement everything. That exceeds the funding that is available for bosque and riverine restoration in the settlement. So comprehensive long-term funding strategies will need to be developed. We should consider how to leverage existing settlement funds to secure additional or matching funds. With that, thank you to everyone for the opportunity to present. We hope you are interested in hearing about the technical challenges as well as the collaborative work with the multi-agency team to develop solutions for restoration, fish passage, and sedimentation. And with that, we have a few minutes and we'll happily stand for questions and comments.
Great job. Thank you very much. One of the things, and I might have not caught it well, but you had mentioned that the Pueblo tribe wasn't necessarily interested in the silverfish. They're more worried about unsightly, invasive plants. I don't know that those were your exact words, but is that generally the opposite of how you find or would see that situation go, or?
Well, each tribe, each Pueblo tribe in New Mexico is their own unique leadership and governing style, and so their concerns will be different. I think, there's maybe a sense of like, we didn't do anything to the silvery minnow, or, before fall, the flood regulation went in, the river would go dry every year, and the silvery minnow did fine. And so there's that sense because they've been there on the Rio Grande for thousands of years. And I think there's just the sense of like, we enjoy singing an open cottonwood gallery. We enjoy seeing turkey. Like, it doesn't mean as much to us that you get excited about a little yellow bill cuckoo nesting. So it's a matter of being able to bring what's needed through the Endangered Species Act together with what the Pueblo prioritizes. Not that they're opposed to the Endangered Species Act.
Sure.
It's just different priorities within the community there.
Definitely. And obviously you guys have a really good relationship with the Pueblo tribe, and assume you have, obviously, since, Tetra Tech's all over the place, have a really good relationships with other tribes throughout. So is that a unique relationship, with developing with the tribe outside of maybe some other clients that you work with?
Yeah, I would say we have probably one of our closest in New Mexico, one of our closest tribal relationships with the Isleta Pueblo. Part of that is their proximity, but part of that is the sedimentation challenges and the environmental challenges they face kind of overlap the skill sets that we have in that part of the world. And so we've been really fortunate to work with them.
That's fantastic. Well, excellent. Great presentation. Thank you. And I didn't know, Brad, were there any other questions out there in the audience?
I didn't see any. I guess I just kind of had a general question for Dave and Kyle. Did working on this project change your perspective on physical versus numerical modeling? It sounds like you kind of, for this project, you had to use a combination of both and really relied heavily on the physical model for it. Is that kind of what you think, for similar projects like this, you definitely need the combination of physical and the numerical modeling?
Yeah, I'll jump in on that as, yeah, certainly humbling for me to think that despite the cost of a physical model, that the value that could be derived. And one of the things, if we hadn't been able to do any modeling on this project, the next diversion dam upstream on the river had kind of a curved, like a quarter of a circle inlet to the sluiceway. The idea was that the hydraulics through that curve would induce a helical current and push sediment toward the inside of the curve so you could decant cleaner water to the outside of the curve. And seemed like it made a lot of sense. And as we mocked that up and put it into the physical model, it was actually one of the only options we looked at that was hands down worse than the baseline or the existing conditions. We said if we were trying to clean the river, this would be the best way to do it, to pull the sediment into the canal. So with some of the limitations in just our understanding of turbulence and the complex processes with the hydraulics, the physical model turned out to be the linchpin for the incredible savings that were able to be realized. Like Kyle said earlier, we wound up, the guys at the lab said, we've been doing this for 20 years, and this is the first time we've seen it where the cheapest and the least complex solution is the best one. It performs the best. And he said, a lot of times we have clients that are willing to pay a little bit more for a solution because it reduces some complexity or it works slightly better. But they said in this case, just fascinating to see that the cheapest and most effective solution is the one that is going to provide, we expect, provide the best reduction in sediment in the canal systems. So the physical modeling, despite the cost of itself, it paid off in spades.
I still think it's like you got to evaluate it on a case by case basis and try to understand what's driving the problem and if that can be answered with a numerical model, because it is always going to be more cost effective to develop the numerical model if you can.
Got it. Thanks so much for that perspective. And I don't see any other questions at this time, so I guess I'll turn it back over to you, Thad. Thanks so much, guys, for the presentation today.
And I guess I would say that lends itself into you guys is that generally people aren't pushing the most cost effective or the least cost way, and you guys led into that. So that tells you a lot as an organization that you're looking at those things and not trying to necessarily upsell something that's not there. So kudos to you guys for that, for sure. Looking out for the client, that's a huge, that's big. So really appreciate your guys' time today. Excellent job. For the audience, David and Kyle's, you have their emails. Please reach out to them, ask them questions. It's an exciting project. Appreciate your guys' time today in the audience as well. With that, we'll say thank you and have a great weekend.
Thank you.
Thank you, Thad. Thank you, everyone.
Thanks, guys. All right, Brad, I think there are 25 people in that one. It's good. Good group.